And now we'll have our last talk here in New York for this session, which is 15 minutes. And after this talk, we'll have a little bit of time for residual questions from the 3-minute talks. But first, Gemma's going to tell us about subhalos and neural likelihood ratio estimation.
Thank you. Hi, my name is Gemma, and I am a PhD student at Harvard. Today, I'll be telling you about my work on probing subhalo properties from strong gravitational lensing images using a simulation-based inference method called neural likelihood ratio estimation. This talk will be based on 2 works I did with collaborators Sid Mishra Sharma, Chansung Gu, and my advisor Cord Dworkin. There are 3 main ingredients that went into this work, as highlighted in the title here. And I will spend the bulk of my talk discussing what each of them means. And before that, I'll start with a brief motivation of why we care about this problem. And then later on, I'll talk about modeling details as well as our results. And I'll end with a brief summary. So the question that we're interested in answering here is, what is the nature of dark matter? If we look at different dark matter models, they offer different predictions on subgalactic scales. So over here, I'm showing an example of the same dark matter halo, but under 2 different simulations. One assumes the cold dark matter model, the other one assumes the warm dark matter model. And as you can see here on these scales, they have very different distinct features. So by looking at these features on subgalactic scales, we can probe the nature of dark matter this way. One of the challenges for looking at these scales is observables are typically complicated by baryonic processes, which are poorly understood and very difficult to model. Luckily, we have these small structures called subhalos that live in a main host halo, and they consist of primarily dark matter, and they lack luminous matter, which means that they don't have complications caused by baryonic effects. So by looking at these subhalos, we can distinguish between different dark matter models potentially. So because these subhalos are mainly dark, one of the only ways of looking at them is through their gravitational effects. So the observable that we looked at is strong gravitational lensing. So in these strong lens systems, we have 2 galaxies aligned with each other, and the light produced by a background galaxy gets gravitationally distorted by the gravity of a foreground halo, which we call the lens. This process produces images that look like that with characteristic lensed arcs as shown in red in that image. So by looking at these lensed arcs in these images, we can deduce properties of the matter distribution in the foreground lens. And this includes any subhalos that live inside the foreground lens as well. So let me just give you an example of how looking at these lensed arcs can tell us about properties of subhalos. So here I'm showing an image without any subhalos in the foreground lens. But if I put a subhalo around one of the lensed arcs, over here as the red dot, we can see a distinct perturbation around the subhalo in the lensed arcs. Of course, here I put a very massive and very concentrated subhalo there just to show you the visual effect more distinctively. In a realistic setting, we won't be able to see these perturbations by eye, but we can constrain them through their statistical properties. So the particular property of subhalo that we cared about that had implications for dark matter studies is the density slope of subhalos. So in a previous work by my collaborators, they showed that with finite image resolution and noise level, the density profile of a subhalo can be approximately fitted by a power law, which means that the rho scales as r to the minus gamma, where gamma is the power law factor, and it's the parameter that we care about. In traditional method of analyzing these lensing images, it's expensive to constrain this parameter because you have to model the image directly, and you have to constrain all the parameters that go into modeling jointly with sampling. And it's also restrictive because you usually only focus on the most massive subhalo, because adding more subhalos into modeling is very expensive and increases the parameter space significantly. So that's where machine learning comes into play, because as we get more images in the future with surveys, to be able to analyze these images efficiently and optimally is very important. So the machine learning method that I used for this work is called likelihood ratio estimation. So the idea here is if we start with some parameter gamma, with the simulator, we can produce images with the underlying gamma. These images are labeled as X, and then we can obtain data pairs of gamma and X. From these data pairs, we can get samples from two probability distributions. One is the joint probability distribution, and the other one is the product, the marginal distribution. And if we have a perfect classifier that can distinguish between samples from these two distributions, we can get a classification score S over there, which tells you which probability distribution a sample pair most likely comes from. And this classification score happens to be in one-to-one correspondence with the likelihood ratio between these two probability distributions. You can imagine if you have a sample pair, the higher the likelihood ratio, the more likely that it comes from the joint distribution instead of the product marginal distribution, and the more likely that your input gamma truly underlies the given image X. So one advantage of this method is that it allows us to combine observations very efficiently if they share the same gamma value. So simply we can just take the likelihood ratio between many different images to get a joint constraint. So in the neural network setting, we basically replace the classification task as a neural network. And it so happens that the correspondence between the log likelihood ratio, log R, and the classification score S is related by a logistic function. So that basically means if we put the last layer as a sigmoid activation in our neural network, we can read off the log likelihood very easily. So here's the method that we use. I wanted to spend a little bit of time talking about how we produced our training set. So there are three main ingredients that go into producing a mock data for each gravitational lensing image. The source, we use a pipeline PELDAS developed by Sebastian Wagner-Carina. And this pipeline filters out some of the well-resolved images from the HST Cosmos survey, galaxies. And for the lens, we model as an elliptical parallel with additional complexities. And we also added in subhalos and line of sight halos. And on the observation side, we added Hubble Space Telescope instrumentation configurations. And we put together everything with the Lenstronomy pipeline. So in terms of modeling subhalos and line of sight halos, in the training set, we model them as an elliptical parallel EPL profile, which gives us access to the true underlying gamma for each image so that we can pass in the label while we're training. But for the test set, to validate our model, we modeled the subhalos and line of sight halos with an FW profile. This profile is parameterized by two parameters, concentration and mass. And the concentration and mass are related in our mock data by a cold dark matter mass concentration relationship. So to validate our model under different population slopes for subhalos, we kind of artificially produce these sets by multiplying the mass concentration relationship that we use by some factor, which we'll later use as concentration multiplicative factor. So here I'm showing you three examples with different factors just to show you how the slope varies with different factors on the mass concentration relationship. So once we have our training set, we pass them into a ResNet 50 model. And the label gamma that we used, we passed it into the dense layer after the convolutional layers of the ResNet. And at the end, we have a sigmoid projection. Once we train this as a classifier, we can read off the log likelihood before the sigmoid projection. And at test time, what we do is we pass in an array of gamma values at the beginning so that we can obtain log likelihood values at each of those gammas in the array so we can get a profile. And the point with the highest likelihood gives us the maximum likely estimate for the gamma. And we know that the log likelihood ratio follows a chi-square distribution, so we can obtain the errors that way by assuming a chi-square distribution. So here is kind of what we got for our validation. So if we use EPL models where we know the true underlying gamma, for individual images, if we compare the true and predicted after we train our model, we see that the error bars are kind of large, but they roughly follow the diagonal line here. But if we combine a set of images that share the same true underlying gamma, the error bars get much smaller and improves the constraints a lot. So this is just kind of showing that our model was working after training. And we did another validation by using NFW and truncated NFW profiles. So here is the concentration multiplicative factor that I was referring to before. So this basically multiplies the CDM mass concentration relationship by a factor. And as expected, we see a higher slope for more highly concentrated subhalos when we put in. And for the truncated NFW, since we have a truncation near the outer area of the density profile, we should expect the slope to be higher, which is what we see here. So if we take the factor as 1, that gives us the cold dark matter predictions, and we take those intervals to put on the right-hand side, and we take a set of 13 HST observations and put them through our model. And the pink curve is the likelihood ratio profile that we got after using HST observations. And we can compare that with the NFW and truncated NFW profiles using mock images. The NFW result is very far away from the observation because they're not a realistic description of subhalos, because subhalos usually experience tidal stripping in the environment. So truncated NFW is actually a more realistic description of their density profiles. But we still see that the HST observation produces a slightly higher slope than what we predict from CDM. So let me just conclude here. So basically in our work, we showed that the likelihood ratio estimation method is an effective and efficient way of probing subhalo properties in strong lensing images, but more still remains to be done. For example, we could look at in more detail how the slope predictions will vary under different dark matter models. And there could also be selection effects that go into account here. For example, more concentrated subhalos are more likely to be observed from observations. So with that, let me end here and take any questions.
Great. Any questions in New York? Yeah.
Did you have a chance to explore how some of these slope results you get depend on your assumptions about this overall subhalo population, like their number or the ratio of their masses?
Right, so the number, we actually have a uniform prior. So during our training, we put in a random number from a uniform interval. And actually the training and testing, we used a different total number, like the slightly different interval, and that had no very negligible effect on our results. Yeah.
Okay, thanks.
So that's something that we already addressed in our modeling pipeline.
So the truncated NFW profile that you are using, I mean, even hydrodynamical simulation are in agreement with this, or, I mean, I'm not very familiar with this. So, I mean, I guess people usually look at M-body simulations for this and see, what is the density profile. So what is the reason of using this truncated NFW profile?
What is the motivation? Or?
Yeah, it's coming from hydrodynamical simulations, or is really an empirical model?
I think NFW is more, so there's not quite, because I think hydrosim, I think part of it is coming from simulation, that we know it's more tidally truncated, but it's not like, you still have to make a choice for what kind of truncation that you use, and that's very difficult because we don't know very well. So I think this goes as far as how we model, how we make the modeling assumptions. And obviously this truncated NFW profile, the interval will look slightly different depending on your modeling assumptions as well, yeah.
There were also 2 related questions to that on Slack, asking how good that assumption is for an individual halo, and whether you subhalo, I mean, and whether you've tested how much that assumption may otherwise bias the inference.
For the truncated NSW.
Yes.
Yeah, so for our purposes, we did not explore extensively how that would like how much that would affect the interval results. But I think it would definitely have an effect just because that we looked at NFW and truncated NFW, there's already a pretty distinct difference. And I think that would be a very interesting future direction as well, just to, it also falls under the looking at different dark matter models and explore exactly what kind of effect it would have. Yeah.
Any questions from Paris?
No, Paris seems a bit asleep this afternoon. Sorry.
All right, maybe they'll wake up in the next session. Does anyone have any questions left over from the 3-minute talks that they've been holding on to very tightly? Okay, great. Well, let's wrap up this session, at least on our side over here. Is there anything else that needs to be announced?